So the linear regression model, it can be summarized as this statement: y conditional on x is normal with a line that's a straight line function of x, and with an error standard deviation sigma. So where these y values are independent and they're not identically distributed, they're independent. So that one-line statement tells you everything you need to know in linear regression. But there's four key, it can be broken down into four key assumptions. The first assumption is that the conditional mean is a straight line function of x. So the mean of y is linearly related to x. The second assumption is that the errors are independent. Or another way of saying that is that the y values are independent conditional on x. We need the errors to have the same standard deviation or the same variance. Sigma is the standard deviation for error. We need that to be the same value for every observation. We need the errors to be normally distributed. So there's four assumptions in there, four assumptions we need to make in linear regression. They look kind of familiar. We've been making independence and normality assumptions pretty much all the way through the course anytime we did inference. The equal variance assumption is also something that we've seen before in two-sample testing. The new assumption here is linearity. Like if we were doing linear regression, we want y to be a linear function of x, otherwise there's no point. So how important are these assumptions? Linearity, obviously, it doesn't make sense to fit a straight line to data if it's not a straight line. So that's the first thing that we need. Independence, as previously, independence is critical for inference. So if you want to make inferences about the true slope based on a sample estimate of it, we need independent observations, otherwise our standard error estimates are all too small, usually, or they're all wrong anyway. Equal variance we also need for inference. If the variance is not equal, if the errors sort of have larger variance at some points than others, that will affect the standard error of the slope. Normality is not such a big deal. So as previously, the central limit theorem gives us robustness to violations of the normality assumption. So that assumption only really matters in small samples, and what we really worry about is strong skew or outliers. And basically, you shouldn't be using a least squares approach if you've got strong skew or outliers. Instead, you should probably transform your data first before analysing it, or use a different model. There is one exception where normality is important, that's when predicting new observations. We'll talk a bit about that later.